Hi everyone, my name is Qingcheng Yu, and my topic is resource allocation for vehicle platooning in 5G NR-V2X network with DQN. This is a presentation for course EECS 6892 reinforcement learning. So before we talking about the method, let's say what's the problem we would like to solve. The vehicle platooning is one of the advanced service with autonomous driving technology. However, in the current general schema, high collision probability of platoon communication, especially in the out-of-coverage area without base stations, which makes the safety of the automatic driving cannot be guaranteed. So we want to solve this problem. Before we talking about the method we use, let's go over some background knowledge that will be helpful for us to understand the project in detail. So first is, what is vehicle platoon? The vehicle platoon is a method to driving a group of the vehicles. The vehicle at the very front of the platoon controls the speed of the whole group vehicles, and it's called a platoon leader. It coordinates the movement of a group of platoon members, which is follower vehicles, by broadcasting basic safety messages, such as the vehicle speed, location, and the directions cyclically. Another knowledge you should know is new radio V2X. So what is it? The new radio V2X, NR-V2X, refers to a vehicle-to-everything communication technologies, which designed in 5G phase standard, which is 3GPP release 16. So what is 5G? 5G is a fifth generation of mobile networks. So it is a new global wireless standard after 4G networks, and it has better performance than 4G network. So it can support the advanced service such as vehicle platoon, which we are focusing on this project. So we use 5G for our communication technology. Then let's talk about the different scenarios. There are two side link models in NR-V2X model. The first is vehicle communication within coverage of base station. You can see the figure in the left-hand side, the blue circle, which is the range of the base station. Another one is vehicle communication out of the coverage, which is the yellow circle that without the base station. So why we focus on the out of coverage scenario? The reason because the current general resource allocation schema for out of coverage scenario is just randomly select. However, this randomness can make a high collision probability because it cannot solve hidden terminal effects and resource selection collision problem effectively. So according to the problem we mentioned before, the motivation for this project is first, solve resource allocation and decision-making problem for platoon communications exceeds the coverage scenario. Second, we will propose a new algorithm. In this project, the reinforcement learning will be used to improve the reliability of communications in connected intelligence transportation system. So before we deploy the reinforcement learning algorithm, let's discuss the road network environment setup. According to the figure shows, this is a finite length multi-line highway where one platoon with length d in unit kilometers. There are also broadcast vehicles and unicast vehicles. They are all considered to share the same resource pool for vehicle communications. To reduce the computational complexity, we would like to change this two-dimensional scenario to one-dimensional scenario. So we map this figure to the one-dimensional. So in this case, the location of each vehicle is assumed to be uniformly distributed. We can see the R is the radius of the communication range of each broadcast vehicle. And this is the platoon leader, which in the red circle, and the remaining vehicle in red circle are platoon members. The length of this platoon is D. We can see also the interterminal range of the platoon leader is also has a length D. So because we want to reduce the collision probability, we need to know what is it. So the relation between the communication range of platoon members and platoon leaders can be summarized, which we know the R denotes the communication range of PM and PL, and M, which is the index of the PM number. And we said M is the last PM index. So the communication range of the PMs is a subset of the union of the communication range of last PM and planetary 2. So according to this, we can see in a one-dimensional finite line scenario, the last PM suffer most from the hinder terminal effect among all PMs, which determine the collision probability of the plan-to communications. So we will focus on the last PM and the plan-to leader. Then we also need to consider the NR-V2X system, which is communication systems. In the figure on the right-hand side shows the VRB maps of resource allocations for plan-to communications, because we only care about the plan-to leader and the last plan-to members. The T, which is set to be the transmission period, and the broadcast vehicle, and the PL, which can generate the BSM every transmission period. So this transmission period is separated to many blocks. These blocks are virtual resource blocks, VRB. It is an abstract resource which is used by the scheduler to define the allocations, and each VRB can support one BSM transmissions in one slot. There are three types of VRB. The red and red cross one, which is busy VRB, white and white cross one, which is idle VRB, and white cross and red cross, which is available VRBs, can be selected. So we can see the VRB maps of resource allocation for plan-to communications in one transmission period. The available VRB selection in current transmission is correspond to the idle VRBs that's sensed from the last transmission period. So we can conclude the leading facts in the collision. The resource selection collision will occur when the broadcast vehicle in the communication range of PL select the same VRB as the previous period. And the hidden terminal effect generates when the broadcast vehicle in the hidden terminal range of planetary leader select the same VRB as before. Then we can define a probability P, which is resource keeping probability. It is the vehicle continues to keep the current VRB selection. Respectively, the probability 1 minus P, which is a vehicle selects another idle VRB before at the beginning of the semi-persistent period starts. Then, after we define the environment, we can now do the Markov decision process before we deploy the reinforcement learning algorithm. The agent of this project is planetary leader, and the environment is one-dimensional finite line described before. So the agent takes an action, and then environment updates the given actions, emits observations and rewards. Then agent receives observations and reward, and to generate the next action for next states. So in transmission period, the action is a subset of action set of all VRBs in one transmission period. And also because the action is determined by the previous transmission period, it is also a subset of the action set of the VRB censored idle in previous transmission period. Then the PL will observe the received feedback. It can be one of ACK and NACK before the ending of the period. ACK, which means the receiver has successfully received the information, and NACK means that the receiver failed to receive information. Because we know the action and observations, we can denote the tuple of combination of these two to demonstrate the state of our MDP. So the state in this project is a combination of historical selected idle VRBS, as well as its observations, which is the tuple, over previous M transmission period. So M, which is what we determine. Finally, the reward is determined by the observed feedback. If we observe ACK, the PL will give a positive reward. If we observe NACK, it will give 0 reward. So after finishing the MDP, we can create DQN to training the model. So in DQN, in each transmission period, the PL will gather a historical action of previous 16 transmission period to build our states. So this state contains 16 previous transmission period, and we use state as input for the neural network. And the first layer, which is convolutional 1D with the activation function ReLU. And the next layer, which is fully connected, which means the planetary leader can see all other vehicles in their communication range. Next layer again, convolutional 1D, and next again, fully connected. And finally, last is also fully connected. Then we will get the Q-learning for different actions. So we select the VRB with the highest Q-learning provided from the neural network. It is the Q-learning method. Then, according to that, we can get the action and reward. So after finishing the DQN, the paper do the simulations for these situations. So they use MATLAB to conduct Monte Carlo simulations for all broadcast vehicles. And also, there is a dataset that is used to test the analysis model for the planetary communication resource allocation and to validate the simulation architecture. It is used to check whether or not it is right or not. So this is the result. The left-hand side figure. It contains an analysis, and simulations. It is clear that the simulation results are consistent with analytical results in different parameters. And we can see when the keeping resource probability P fix the same, and the vehicle density increase, the collision probability will also increase. That's because the number of vehicle increase will cause the hidden terminal increase. Another case, which is when we fix the vehicle density and increase the value of P, collision probability is also increased. That's because the vehicle in the higher value of P will be more likely to choose the same VRB as the PL chose in previous transmissions. Here is my result get from the data. I use the data set, but not the simulation, because simulation is conducted by the MATLAB and it's hard to deploy. But the result I get is similar. So you can see the result figure in the right-hand side. The collision probability gained from the DQN is lower than the random selection algorithm. So we can conclude that through applying the reinforcement learning, the PL can learn from its interaction with the communication environment where, and actually it can improve the communication reliability based on the DQN. Now, here are some another result gained from the paper by conducting simulations. We can go over this one and see what's the result. According to the result, the collision probability applied by DQN is always lower than the random selection algorithm in different vehicles. The vehicle densities, you can see. Also, the increase rate for the DQN is lower than the random selection for different parameters. And also, we can see as the vehicle density increase, the collision probability also increase for both cases, but the DQN is still lower than random selection. Moreover, another thing that we found is the DQN is not sensitive to value of P, which is the probability that keep the same VRB as the previous communications period. That shows we do not need to consider if current VRB is available or not, because it will not affect the decision we're making. So in conclusion, this paper solves the resource allocation and decision-making problem for planetary communication exceeds the coverage scenario by utilizing 5G, which is new global wireless standard mobile network, and also the reinforcement learning. The DQN as a reinforcement learning method we use can effectively improve the resource management and communication reliability compared to traditional methods randomly selected. This is the result and conclusion we get from this project. Here is the reference. Thank you for watching.